Imagine that we are doing a double slit experiment. So we have, we fire a bunch of electrons or some photons through two slits, and they form a diffraction pattern at the far end, and they interfere. So we see a nice interference pattern at the screen behind these two slits. That's a coupling between a quantum system and a classical system, because we treat the two slits as classical. We treat the screen at the back as classical, and there's this little photon gun which is firing photons or firing electrons, and we treat classically. So, or a particle in a potential. We treat this potential that's sitting there. That's like a classical potential, which is produced by a magnetic field or something like that. We treat that as classical, and the particle moves
I see.
So that's an example where the classical system exerts a force onto the quantum system. And we do that all the time in physics. So we know very well how to couple a classical system which acts onto a quantum system. What we didn't know how to do, except for these examples that, there were these examples in the 90s, which, curiously were not, I don't think, really known, except in a very small community. So what the question that you want to address now is, can a quantum system back react onto a classical system? Can it exert a force onto a classical system without causing a contradiction?
Mm-hmm.
And there were arguments that were given as to why that will always result in a contradiction. And I think the most famous argument is due to Feynman at one of the first Chapel Hill conferences, these famous conferences that were organized to discuss general relativity.
Actually, on this channel, there's a documentary on the Chapel Hill conference, particularly with anti-gravity's connection with quantum gravity.
These famous conferences that were organized to discuss general relativity. And the argument was as follows. He imagines a double slit experiment, and he imagines this particle, which, sometimes you could imagine a particle which goes through slit number 1, and sometimes it goes through slit number 2. And then he says, well, imagine that this particle has a gravitational field, and imagine that we measure this gravitational field, and imagine that we can measure the gravitational field to arbitrary accuracy. Then we could, by measuring the gravitational field to arbitrary accuracy, we can discover where this particle is, because we measure its gravitational field. And then we would know if it went through the left slit or the right slit.
Mm-hmm.
And if we know whether it went through the left slit or the right slit, then we shouldn't have an interference pattern. Yet we see interference patterns, and therefore Feynman argued that we would have to quantize the gravitational field.
Why can't someone say, look, we've never done that experiment where we've detected gravitationally whether it's gone through A or B. And if we were to do that, we would see that there would be no interference pattern.
Right. That's a good question. And it turns out that if you merely try to write down the state of a quantum system and a classical system such that the classical system knows which slit the particle went through, then that's enough for you not to have an interference pattern. So whether or not you measure the gravitational field, the mere fact of the gravitational field knowing which slit the particle went through would be enough to cause the interference pattern to not be there. And that's the same with, people often ask about quantum theory, do I have to look at the cat, whether it's dead or alive, in order to collapse it? Does a person have to look at it? Well, no, just the environment measuring, the environment measures the cat. And here the gravitational field is measuring the cat and is measuring which slit the particle went through. So if your environment is classical, then just the fact that in theory it could be measured to arbitrary accuracy to determine which slit the particle went through, that would be enough to destroy your interference pattern.
Thus, the conclusion is that the particle's in a superposition, like even a gravitational field is in a superposition?
Yeah, that's what Feynman concluded, that the gravitational field had to also be in a superposition with the particle. That was the only way to consistently think of the double slit experiment in which the particle produced a gravitational field, because it was a massive particle. But if you, and maybe this is in part comes from thinking about things from a quantum information perspective. We're very, one thing that we've learned about quantum theory is that the state of the state of the wave function, the quantum state, is more analogous to a classical probability distribution than it is to, say, a single C number or a single position and momentum of a particle. So one way to think of it's a good analogy. The ket of a quantum state is a bit analogous to a probability distribution, and because we think about probability distributions all the time in quantum information theory, it's quite natural to think about Feynman's nogo argument and to just say, well, wait a second, what if the gravitational field is in a probability distribution of different configurations? Then measuring the gravitational field will not determine which slit the particle went through. So, for example, if the particle goes through the left slit, it might produce some slightly random gravitational field. And if it goes through the right slit, it will produce a slightly different random distribution of gravitational fields. But because we have a random distribution of two different gravitational fields, measuring the gravitational field does not determine which slit the particle went through.
Is a C number supposed to be thought of as a scalar or a complex number? Like C stands for what?
Oh, sorry. Yeah. So I guess in this case, when I talk about a C number, I just mean that I guess this is in, say, the context of looking at Einstein's equation, where you have an operator on one side, and then it's just a number, the Einstein tensor on the other. So it's a single number versus an operator, or say a vector, which is, in quantum theory, observables are operators which act on quantum states, which are vectors, whereas in classical mechanics, we just have, the result of a measurement, a particle is just described by a number. This is the particle's position and momentum.
I've heard the term C number. I've heard it, but I've never read it. So I don't know what is the definition of C number. Right. So what's the difference between classical randomness and quantum randomness? You mentioned it before, but can you briefly outline it once more? Because you're about to make the connection between, you're about to explain how randomness solves a harmony issue.
Right. So a quantum system, so a classical system can have a probability. So we can imagine, for example, a particle has a position and a momentum, and we can also imagine that we have a probability distribution of different positions and momentums. So, there's some probability that the particle has position x equals 0 and momentum, 10 units. Yep. And we can imagine such a distribution, and the probabilities, both of its, of particular values that the position can take and the values that the momentum can take, those are all positive, and they all sum to 1 if we were to sum them up. On the other hand, a quantum state, we cannot ascribe probabilities to a particular outcome of a position and a momentum measurement. That just doesn't exist. Because we're either going to perform the position measurement or we're going to perform the momentum measurement, but we don't perform both. And so the quantum state does not need to be described by a probability distribution over position and momentum whose values are all positive. It's describable by something else, which is, it can be described, for example, by something called a Wigner distribution, which looks a lot like a probability distribution, except its values are not always positive. And that's okay, because I will never measure and get a negative probability, because I can't measure both the position and the momentum of the particle. So it's okay if a quantum state, if its distribution has negative values. That's not okay for a classical distribution. It has to always have positive values, because the probability that a particle has a particular position momentum needs to be positive.
So now what's meant by that the coupling between gravity or some gravitational system, some classical system, and some quantum system has to be stochastic. Also, can you outline what the difference between randomness and stochasticity is?
Okay. I don't know that there's so I use those words interchangeably. Maybe there's a more technical terminology, and maybe they do mean different things, but I tend to use them interchangeably. Um, uh, Although I guess when I think of a stochastic process, I think of a dynamical process. So, the particle is going through the left slit, and in a deterministic theory, it would bend space-time in a particular way.
Mhm.
And in a stochastic theory, it would, it almost like flips a coin, and depending on the value of the coin, it bends space-time in a slightly different way. So you can imagine that there's these coins being tossed all the time, which determine, so the particle goes through the left slit, and it produces some, different gravitational fields with different probabilities. And if it goes through the other slit, the right slit, it will produce it'll bend space-time in some other way, but the way in which it bends space-time is determined not just by which slit it went through, but also by it flipping a coin. Now, I want to be careful when I say flipping a coin, because that one is almost imagining that there is some physical process by which it determines which of these gravitational fields to produce. But actually, I don't believe that there's actually any physical process which is determining which gravitational field is being produced.
Let's make it simple and imagine that someone's walking through two doors. Does that mean that they're constantly carrying with them a coin, and even before they encounter those two doors, they're flipping it and they're making some other decision, and then when they get to the door, then they flip it, and then it's a left-right decision? Is this coin just being flipped for them? How does this work? There's no physical process?
Yeah, I mean, maybe even another way of saying it is, imagine that someone's going through the right door, someone goes through the right door or the left door. If I'm far away, I can sit there with a pendulum, and I could actually try and figure out which door they went through by trying to measure their gravitational field. But now imagine that at every point in space, the gravitational field is just fluctuating randomly. So it's as if, it could have one value, but someone just goes and randomly makes that value be slightly higher or slightly lower. And so at every point in space, you kind of can imagine that there's this noise, this randomness, which somehow is affecting the gravitational field and making it very difficult to measure and determine exactly what the gravitational field, whether it's being produced by the person who's going through the right door or the left door.
Okay, then the way that I'm imagining it is that you have a pendulum, and I don't know how the pendulum apparatus is supposed to be when you actually measure, but I'm just going to say that it's completely still. And then you see, does it move slightly to the left or move slightly to the right, because it's attracted to the person who goes to the left or to the right?
Right.
Okay. You're saying that actually, if you were to look at that pendulum, it would be constantly jittery, because just even without anyone going through the doors.
Right.
Oh, okay. So what I was about to say is, could this not be solved with more precision, but then you would have to do a series of measurements?
Yeah. So, I mean, the most famous gravity measurement is probably the Cavendish experiment, where they sit there with this, beam with two weights on the end, and it's held up by a string, and it kind of rotates like this, and you use that to measure, say, the gravitational field of the Earth, or of two balls of a kilogram mass, for example. And if you ever have seen that experiment, or you've tried to do it in, say, an undergraduate physics lab, you'll see that the torsion pendulum kind of moves about quite a lot, and is jiggling much in the way that we just described. And the reason it's jiggling is mostly because air molecules are hitting it, and the system is very noisy, and there's heat, and we don't have very good control of gusts of air, which push and pull the pendulum. But imagine that we got rid of all those gusts of air and had everything in a perfect vacuum, and didn't have any stray electromagnetic fields or gravitational fields around, but we cleaned up everything. Would there still be some fundamental noise? And this theory predicts that there will be. And it's this noise which somehow allows interference patterns, because the gravitational field, because it's random and noisy, it doesn't allow us to really determine which slit the particle went through.
Now, the quantum field theorist would say there is noise anyhow because there's some fluctuations. So is there a way of you distinguishing the noise from the fluctuations versus, I don't know what type of noise this is called, but this post-quantum noise?
Yeah, that's a very good question. And there is disagreement. So, I've had disagreement with some of my colleagues about this. But we've calculated how much noise there has to be, and there has to be a lot more noise if gravity is fundamentally classical, there needs to be a lot more noise in the gravitational field in comparison to the quantum case. And it's true that in the quantum case, you also need some noise there, because you can imagine the same experiment, the double slit experiment that I just gave. You can imagine the same argument being made about the electromagnetic field. How is it that if the particle goes through the left slit or the right slit, I can measure the electromagnetic field, and what is it about the electromagnetic field which doesn't allow me to determine which slit the particle went through?
So what is it about the electromagnetic field?
Right. Well, it's as you say, it's the fact that there is, we can't measure the electromagnetic field to arbitrary accuracy. I can't measure because the electromagnetic field has a quantum nature. Then I can't measure with exact precision, the electromagnetic field and say its conjugate degrees of freedom. So because we can't measure the electromagnetic field to arbitrary accuracy, we're not able to determine which slit the particle went through. Or another way of saying it is this: in quantum mechanics, you can have two different states which cannot be distinguished. In other words, the electromagnetic field will be in a different state depending on whether the particle went through the left slit or the right slit. But even though the state of electromagnetic field is different, I still can't tell it apart. It has, some overlap. Both states, there's overlap between the two states, and those two states are not orthogonal, we would say. In other words, they can't be distinguished perfectly. And it's because those two different states of the electromagnetic field are not distinguishable. It's that which allows you to still have an interference pattern. Now, sometimes you don't, right? Sometimes the particle will go through the left slit and it will emit a photon because it happened to hit the wall in a certain way. And if I were to measure that photon, I would be able to determine which slit the particle went through. So there is some decoherence. The interference pattern does get disturbed a little bit by the electromagnetic field, but not by very much.
This theory of yours doesn't have predictions. So one prediction I see is that it's a null prediction, namely that there is no graviton.
Right.
Does it have other predictions? And am I even correct by saying that there is no graviton?
Right. There's gravitational waves, but there is no, quantized particle which is responsible for carrying the gravitational force. So one of the big predictions is this noise in the gravitational field. So we predict that you should go and do the Cavendish experiment, and you will have to see a large amount of noise in the gravitational field. Now, the problem is that there is already a large amount of noise in the gravitational field. If you ask the people at NIST who are responsible for keeping the 1 kilogram mass and telling us how, keeping that to, and doing these precise measurements of, say, a 1 kilogram mass, they will tell you that it's actually a very difficult experiment to perform, and that their measurements do have quite a large variance and inaccuracy. So the experiment we're proposing is, higher precision tests of those measurements of, say, a 1 kilogram mass in order to put a bound on how much noise there is in the system.
If you enjoyed this TOE clipping, then the full video is linked in the description. You should also sign up for TOE Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core TOE community. You'll also receive my top 10 TOEs. Think of it as the intellectual version of Quentin Tarantino's Obsession.